decirles, porque creo que vale la pena mencionarlo, antes de dar paso a su presentación, que lo que él inició como un lazo de colaboración entre México y Europa en general, con el Consejo Europeo de Ciencias, sigue vigente y cualquiera puede seguir colocando propuestas en este convenio bilateral, bueno, con la Unión Europea y México, y está abierto todo el año para cualquier propuesta de carácter científico. Bien, vamos a dar la palabra al doctor Dingwell, por favor, para que nos dé su charla sobre el acceso a través de los experimentos a las erupciones volcánicas.
So after all of that, maybe it's time to retire. But unfortunately, I have to do a few more years. Let me, this is the last opportunity on this visit in front of all of you to thank again everybody who was involved in the process of this honorary doctorate. I realize that it is a special thing and that nothing like this happens unless people cooperate for the good of the science. So thank you very much again for that, and I hope that my visits here will continue, will increase in frequency, and each time I come here, I look forward to speaking to as many people as possible. And sometimes when you leave, the result of your conversations lead to other conversations in their wake. So in the spirit of all of us working together, let me introduce you to a topic which I have spoken on before in this city and in this room. But every time I give a talk, I promise you, it's different. It's kind of like being in music and making a performance. So let's see, Paco is happy to hear that. So the first sentence, or the first phrase, experimental access to volcanic eruptions. So you might say to yourself, we have plenty of access to volcanic eruptions. That's the problem. We access them all the time. If we didn't have access, we wouldn't have a problem and you wouldn't have any science here. But of course, what we access is the ejecta, essentially. What we access is the last thrust of these systems, and what we get as samples are cold, they are decompressed, and they are frozen remnants of what was the initial system. And so ever since the beginning of volcanology, the great challenge has been take the products and interpret the sources. And over the century in between, we've had many people who have pointed to the problem of trying to infer the deep processes from the shallow products. Bowen himself, the father of experimental petrology, talked about the enigma of the lost volatiles and how could we capture the volatiles again. So to take volcanic materials and put them back into the volcano is philosophically, I think, easy to understand as a way of investigation. And that means practically to do experiments in the laboratory. And so when I speak of experimental access, I speak of laboratory-based access. In situ, we believe, at high pressure and high temperature on actual magma. This is a propaganda slide to remind us that everything we do about volcanic eruptions is immediately important for understanding the consequences of the eruptions, for understanding the monitoring of the volcanoes, for managing life next to the volcanoes, but it is also scientifically, fundamentally, and centrally a part of the Earth system. And when we talk about the Earth system, as you know, it's basically geoscience, classically, plus the hydrosphere, the atmosphere, and everything else on the surface of the planet. So you see that volcanic eruptions are in a unique place in geology, in geosciences, because they are the conversation, or they are the transport of lithosphere immediately into the atmosphere, the hydrosphere, the biosphere, and so on. When we have an eruption, as I like to say, the ash goes everywhere, goes into all of those places, goes into your lungs, goes everywhere. So actually, I think that the study of the impact of volcanic eruptions and the study of the nature of volcanic eruptions has a very glorious future, because I'm convinced that more and more and more details of how these processes take place will lead to more and more and more understanding, applications, mitigation measures associated with them. So in Mexico City, I don't need this slide. You all know that it's a global problem. In Europe, I do need this slide, because the 500 million Europeans, they don't all believe that volcanoes are their problem, okay? But about 10 years ago, this changed. Because of the eruption of Eyjafjallajökull in Iceland, we had a situation where everybody's transport by air was stopped for about 10 or 12 or 14 days. It cost enormous amounts of money, and everybody that you speak to in Europe who is old enough says, yes, I remember where I was, and I could not go where I wanted to go. And I was on my way to Mexico, and I had to stop that trip because of Eyjafjalla. So it is a global problem. It's everybody's problem, and it's perfectly legitimate to study it in Munich, in Germany, just as legitimate as it is to study it in Mexico City. It's a complicated problem. You all know that. You know it better than I do. But just to remind us that the practical consequences of the volcanic eruptions reach into the environment and into our lives in a multitude of ways, and these are about 15 different potential causes of death of humans in volcanic eruptions. And when I put this up, I always get social scientists excited, I get geographers excited, these people are all struck by the interdependence of all of these parts of the Earth system, by the proximity of infrastructure to these different hazards, and therefore they immediately fall in love with the idea of understanding and managing a volcanic system. So this slide is to remind me to be humble. Most of volcanology by far has always been and continues to be based upon the other two parts of the business, not the part of the business that I'm interested in day by day. The history of volcanology is the history of all geosciences. It's based upon field observations. And so it's a simple analysis of the past history of volcanoes, which gives us the greatest insight into their potential behavior in the future. And this is a logic which will always be there. It's kind of forensic research. If you will, it's similar to having a patient come into your room as a medical doctor, and before you begin to handle this patient or to advise or to prescribe or to operate, you're certainly going to interview this patient and understand everything he can tell you about the past of his symptoms and the past of his behavior, right? So this will always be the core of volcanology. The modern, if you will, incarnation of the same thing, observations, is monitoring. And monitoring is as I'll say in a minute, it's the big business of volcanology. Monitoring is all of the methods which could possibly be imagined for a surface near phenomenon in the solid earth sciences. It's a very exciting place because it is relatively accessible in terms of monitoring techniques. And in the generation that brackets my life, of course, we've gone from virtually no computing power to the doubling of computing power every X months based upon Moore's law of chip development. So we have seen a rapid rise in all of the computer-based modeling, and of course, every day volcanoes erupt in computers all over the world. And then down at the bottom, you have us. We're very few. Maybe 100 people worldwide would dare to call themselves experimental volcanologists, maybe less. When I started, I was afraid to call myself an experimental volcanologist. I thought nobody will pay for this. I better call myself an experimental geochemist or experimental geophysicist or experimental petrologist. But of course, people start to call you things after a while, and so here we are. Experimental volcanology is alive. Just to remind you that the challenge of monitoring, which is consuming most of the resources that we have for volcanology, I think I'm correct in saying that, it's very important, is one of combination of very different techniques and different signals, and of course the interpretation of the signals. And the mechanistic interpretation of the signals is not necessary for volcano monitoring. It's not even necessary to do science of the interpretation of the importance of volcano monitoring, but there are many, many, many people in volcano monitoring. In fact, I probably never met somebody in volcano monitoring who was not interested in the mechanistic origin of what they are looking at. It's inevitable. So this curiosity cannot be stopped, and it's at least a curiosity, and at best, in the future, we have a model of a volcano which contains all of the monitoring data. It's becoming a data-rich field today, thank goodness, and all of the mechanistic interpretation. And the mechanistic interpretation of monitoring needs not only surface observations of the phenomenon, like Plinian clouds, pyroclastic flows, lava flows. It also needs the attempt to monitor the phenomenon inside the volcano. And how can you do it? You can do it with experiments. Yes, you face great challenges because you must decide that the experiment you performed is useful for nature. I always say in geoscience, in experiments, we have it much more difficult than in physics or in chemistry. Perhaps we are the same as biology, I'm not sure, don't know enough about it. But an experimental physicist or chemist, if they do a good experiment, it's reproducible and they can describe it correctly, it's successful. In geoscience, if we do an experiment, it's reproducible, we describe it successfully, it's not yet successful because we need to say that it is relevant to the problem of geology. We have an extra burden. That was told to me when I was 26 and I never forgot it. So we tried to break down the problem into a simplified view of a volcano, so simple that we know it's not completely true, but in stripping down the problem to bite-sized pieces, as we might say in English, we allow answers which we can extrapolate and which we can combine back into an eventual complex model of the volcano. So it takes, you have to relax to appreciate experiments as an audience. You have to accept that we go slowly and systematically, and it's often very frustrating for field geologists to listen to what an experimentalist will tell them because they say, oh, that's fine, but that's not the whole problem, and I need an answer to the whole problem. You've just given me 5%. But if I can give you 5% and it never changes, if I can give you 5% and it's the truth for all time, that's 5% that you can rely on and you can build on. And as you know, much of geological interpretation and cross-sections in geology, this famous or infamous business that we all have of building cross-sections, is based upon less than 5% documentation at depth. It's based upon wisdom, experience, and interpretation. So these are the processes that we imagine must take place in volcanoes. We say this because we get the products. This makes us so different from many other areas of solid earth sciences because we get the products immediately. Nothing has happened to them. We know where they've been. They started here, they went up there, we can even observe it sometimes, and they landed here. So we can cope with what has happened since the eruption, and we can interpret what they tell us about what happened during the eruption. And so we know they must be saturated in volatiles because we see the gases coming out. We know that they must have nucleated and grown bubbles and even come to foam because we get bubbly lavas and we get foamy pumice. And we know they must be fragmented because what we get in our hands are broken pieces of glass. So all of these processes take place, and all of these processes deserve their individual experiments. And the process that I'll say now something about is the key process of explosive volcanism. It is the key event, horizon, if you will, in the sense of the material response of volcanic eruptions. When I say material response, it probably sounds foreign, sounds like it's not volcanology to most of you. That's why I say it, because we come at this volcanic eruption problem from a, as you saw in my interview, from a sample point of view, but also from a materials point of view. And this is what we hope that we have added, that we have given to volcanology. This is why the Coursera course that I give is called Volcanic Eruptions, a Materials Science. So here you see a plot of the basic notion which allows us to design our experiments. The basic notion is very simple. It is the idea that the fracture or fragmentation to form ash, to form pumice, to form pyroclasts must take place on this yellow line. Now the yellow line looks fairly fat. It goes all the way from fast to slow processes, from hot to cold processes. So you may think that's not helping very much, that's not very specific. But in fact, being able to theoretically divide up the response of magma between the brown, which is the flow, the viscous relaxation of magma, the gray, which is the fracture, the brittle disruption, elastic response of glass, and this yellow line between them was actually, when it was stated about 30 years ago today, a great advance in all of this. And the yellow line is well known in industrial processes. It's called the glass transition. It is the basis of the glass industry. And the glass transition, although we normally think of glass as something like this glass, which indeed is a silicate, perhaps with boron in it, nevertheless, we can make a glass out of any liquid. Even the water in this glass can be made into a glass. The fundamental physical process is general, and it is the glass transition. And so back in 1989, we plotted for the very first time the idea that what we were working on in material properties was relevant. There it is, the word eruption. I was very scared when we wrote this paper because I was not a volcanologist, I was a petrologist, and I knew the difference. And I knew that if I went into a paper and wrote eruption, that I was opening myself up because I had no expertise beyond what I read in textbooks. The basic idea was this is the material boundary between flow and failure, the brittle fracture criteria here, and the calculation of the temperature in reciprocal temperature here and relaxation rate or strain rate estimated from the literature was very close to the estimation of the material failure. So it was circumstantial evidence, as you would say in American television, that two things could be related because they're close. They are in proximity to each other. The materials do break where we expect the conditions of explosive volcanism are. And the other thing which inspired me back then, before we finally formulated all this in 89-90, was the simple observations of ash and all of the compendia, for example, of ash by Grant Hyken and other people who had shown that ash were broken glass fragments, unquestionably. And they didn't look like they were broken in a secondary way, which many people believed back then. They looked like they were simply broken once and deposited. So could it be that simple? So the idea was that next to the beautiful crystals that you see here, and the opaque phases here are probably crystals, you also have these beautiful broken pieces of glass, which you would also see if you dropped this on the floor and looked at the broken glass particles in the same size range. Can it be that simple? Now, the problem that we deal with is truly a materials problem because we have a spectacular range of behavior of magma on Earth. I do not know if we have the same range of behavior of magma on Venus? Nobody knows yet. I do not know, but it's probably unlikely that we have the same range on Mars. Most of those lavas are iron-rich, and they will not show this complexity. And so on and so forth. Mercury. The thousands of exoplanets, which we now know are rocky exoplanets, they're probably all volcanic, and someday, perhaps, we will be able to do planetary volcanology in a comparative way. But this simple plot, in German, I apologize, is viscosity versus water content. And because we are on the Earth, the water content that we end up with at the end of the volcanic eruption is not here, it's not here, it's way over here. And as you can see, way over here is a problem. Because look at the dependence of the properties as you approach this side of the diagram. So we know from melt inclusions that we can get large amounts of water before the eruption. We see them in the rocks, in the crystals, in the magma. Huh? But when we look at the matrix glass, we have water contents over here. So we've lost all this water, and as you see, losing a little bit of water is not a problem, but if I lose this water, then my viscosity rockets upwards. And then the yellow line starts to move drastically to higher temperature. I start to make my material be inviscid. I start to end up with elastic responsive magma. Because I've moved the water out into the bubbles, it's no longer chemically dissolved in the liquid dehydrates, the liquid dries out. And because high silica liquids, this is a calcalkaline rhyolite, because high silica liquids show this, we have a crisis, we have a problem, and we have explosive volcanism. Basalt will not do the same thing. And therefore, basaltic volcanism is not largely explosive. The other point, which is drawn from work by others, Papale, Jopar, and others, Sparks, is that when we talk about the conditions of the material as it arises to the Earth's surface, consider this to be 5 kilometers down. This is 5 kilometers down. 0 is 5,000, I apologize. And 5,000 is the Earth's surface. Just look at the lithostatic line and you're okay. So we could calculate a lithostatic load. We could also calculate a magma static load. It would be slightly lower in slope due to the lower density of the magma. It would be slightly curved because the magma is changing its density due to vesiculation. But it would not be drastically different than the lithostatic line. But look at the flow pressure. The flow pressure is revolutionary. It's categorically different than the decrease in the weight of the rock. And the curvature of this line depends upon the variation in viscosity of the magma from wet, where it's low, to dry, where it's high. That gradient in viscosity translates into this curvature in flow pressure. And because this is a volumetric stress, when I'm decompressing here, I get a strong decompression rate. And this decompression rate becomes absolutely critical just before the fragmentation of the magma. So we're actually dealing with very high decompression rates, not because the magma is coming from gigapascals per second, that's of course not the case, but because the material properties of the magma are forcing these high decompression rates to be expressed in the magma. It's a fantastic interplay of these particular materials and the fate that they give to these magmatic properties. Okay, so just two simple video expressions of the ductile to brittle transition. Ductile to brittle is all of volcanology. Ductile to brittle is the difference between magma and rock. And all of your samples are rock, and all of the systems are magma. So you cannot avoid this fundamental central issue of ductile to brittle in volcanic eruptions and in volcanic products. And what you see is a lava flow, which is clearly ductile on a large scale. But of course, if you focus and you look at the blocks falling off the front of the lava flow, then you see individual cooled blocks are no longer ductile, or very little ductility. They are brittle. They're cracking, falling off the surface. Now, this is Etna. This is a just above a basalt and silica content. And Etna, of course, is crystallizing as it dies. And so a large part of the transition from ductile to brittle in this system is because of crystallization. But this one is different. This is onsen in southwest Japan. Yeah, I'd like to turn off that video, but I probably don't have the option. Here we go. Yes, I do. So what happens here is you have a glacier of magma, a glacier of lava sitting on the top of the, I say that all the time and I know people don't like it, but it's the closest approximation to the description of a lava dome that I can think of for non-experts. It's essentially a large viscous mass sitting on the top of the mountain, and then it begins to flow down the mountain by creep very, very slowly, perhaps producing a lava flow. Huh? And what happens in the case of a collapse of this system is the slowly flowing viscous mass fails due to some surface-related structural criterion, perhaps just over-steepening, and as a result, it fragments. And the overpressure in the bubbles of the rock contribute to the energy. Once you give them a little bit of a push over the edge of the strength of the rock, the entire rock disintegrates into massive clouds of dust. And this is the same kind of transition into dust, into ash, which you see in Plinian eruptions. It's just much more difficult to see because in Plinian eruptions it's happening underneath the surface of the vent. Okay. So the whole history of the experimental investigation of these kind of systems is not very long, maybe 30, 40 years. Some crazy experiments were used in the beginning, which were nothing to do with the materials involved. If you look on the far left, you see an experiment where mineral water, CO2 in pressurized water, was used to try to simulate foamed flow of lava as it comes up the vent and out onto the surface. If you look in the middle, you see a device used by Heidi Mader in Bristol where she used potassium chloride solution and sulfuric acid. She put them in two annularly arranged chambers, and she could mechanically expose them through a perforation, cause an explosive reaction of potassium chloride solution and sulfuric acid, and cause a foamed flow. They were doing anything possible, mechanically or chemically, to cause a foamed flow because they believed the foam flow was somehow the key to understanding the dynamics of eruption. And on the right, you have the bomb of myself and Mikhail Alidibirov, 1994, 1995, 1996, when we said, okay, why don't we just stick magma back at pressure and temperature and decompress the magma? Why don't we see if we can make it fragment and see if we can produce ash? That was it. And one day in 1995, Mikhail came into my office with a little bottle about this big of gray ash and said, Don, nature paper, we have just made volcanic ash simply by decompressing a rock. So in order to characterize all these systems, we need to know all the material properties. In order to know where the yellow line is, we need to know the chemistry, and we need to know exactly what the composition dependence of viscosity is. And so you use methods which you normally would never find in a geology department or a geophysics department or even a geochemistry. You use things which you would normally find in a glass department or in a materials department. And this is the high temperature setup with a viscometer, which allows us to measure viscosity. And this is the low temperature setup with a dilatometer, which allows us to measure the same thing. And so we combine data sets, high temperature viscometry, low temperature viscometry. This is the log of the Newtonian viscosity versus the reciprocal temperature. We attempt to see if they are Arrhenian. This one is beautifully Arrhenian, linear dependence on the reciprocal of absolute temperature. It's a calc-alkaline rhyolite. The one liquid of all of these liquids, which are all natural volcanic liquids, the one which is Arrhenian is the one which explodes all the time. Calc-alkaline rhyolite. It's special. It's way over on the left, which means that its viscosity is far higher than the viscosity of anything else which the Earth gives us. Okay? You can imagine that's a lot of work. I hope it looks like a lot of work, because it was a lot of work. When I was a student and I did my first viscosity experiment at the National Bureau of Standards in Gaithersburg, Maryland in 1982, a technician came over to me and he looked at me and he said, Dingwell, he said, how old are you? And I said, I'm 26. And no, I was even early, I was 24. And he looked at me and he was a bit disappointed. He had to change his answer because he said, okay, you may make it. And I said, what do you mean? He said, when you retire, you may have a viscosity model for all of the chemical dependence of viscosity. He was used to telling people they had no chance, of course. Okay, let's take 2 trips across the yellow line, a fast trip and a slow trip, experimentally, okay? We do the fast one first. The fast one is a tribute to this man who is difficult to see, I've been told. There is Mikhail Alidibirov from Kamchatka in Russia, who arrived in Bayreuth in Germany in 1994 and said, let's make a volcano. What we do now is best expressed by these pictures. This is a it's a low temperature and low pressure tank. It runs about 3.5 meters high. And this is the magma chamber below. So we have high pressure, high temperature below the magma. We have something approximating the vent. And then we have the atmosphere above. Okay? So the most impressive thing to see is just the atmospheric tank here. And what you see here is the magma chamber. So this is this. And this is, at this point in time, in the 1990s, this is absolutely standard technology. We just turned it to a new purpose, okay? So here we have a red hot magma chamber. Inside of there's a magma sample. The magma sample is about 22 millimeters wide and about 70 millimeters high. It's enough that you get a characteristic distribution of the bubbles, which are a few 100 microns, and a characteristic distribution of the crystals, the phenocrysts, which are coming up, which are of the order of millimeters. Okay, that's important. So physically, the conception of the experiment is bubbly magma under pressure, air not under pressure. Remove the diaphragm and see what the bubbly magma will do. Just see what the bubbly magma will do. So I'm going to give you 3 characteristics of the results. I'm going to talk about the threshold, I'm going to talk about the speed, and I'm going to talk about the permeability of the system. Gas permeability is central to understanding the stability of volcanic structures. So this is a mock-up at room temperature, which shows you what these materials do when you decompress them. They fragment. Now this is at room temperature. That shouldn't surprise anybody. That's a rock. Okay, I have a rock with bubbles. The bubbles contain pressure. I remove the external pressure. The permeability is low. So the only way that the bubbles can decompress is to destroy the rock. And that's what they do. And at high temperature, in volcanic eruptions, the same thing is going on. Okay? Another picture to show you how well we can envisage, this process. So now it's decompressing. There you see it go. That's new ash. That dust which you see at the top and which you see in all of these particles here is all new ash. We just made it. Okay? So the surface is absolutely virgin. There's no chemical reactions on the surface. And you see how ugly and complicated it can get. And if you can imagine a dome now destabilizing, you can see that the physics of understanding exactly how the distribution of failure will take place will be very complicated indeed. And just a flyby of the last thing, I'm sure you're wondering what it looks like at the top. And this is what it looks like at the top. Here comes the air. And here comes the ash and the lapilli. Okay, so you see we can do high-speed videos and we can watch what is essentially a steady state flow for a few microseconds, a few milliseconds, okay? So although we call this an explosion, by going to high-speed cameras, we can control, we can tame this, we can monitor this, we can measure the velocity, we can measure the deceleration, we can even track individual particle trajectories, all kinds of stuff. We can answer questions like, is there secondary fragmentation when the particles hit each other? Do particles explode in mid-flight? All kinds of stuff, okay? So we can make a science out of it. We can repeat experiments, same conditions. We're on solid ground. Now remember, we're lab guys. Now we're thinking, yes, I don't and only have the ability to make Popocatépetl erupt. I can do it every week for a whole year. Just imagine if you had the choice, right? You really want to understand Popo, or Hugo wants a sample of ash. Imagine he can sit there and press the button, collect the ash as he likes, right? So this is the false sense of power that you get when you run experiments, because you begin to believe it's really the volcano. So this is the threshold. How much does it take? How much pressure decrease do we need turns out to be a fairly small number. These magmas are very fragile. So if you look at a typical value of vesicularity, 60–70% vesicularity of bubble content in a magma, the strength of that against the tensile decompression is only about 3 megapascals, 30 bars. That's it. If you put a 50 bar decompression on a highly vesicular magma, you will destroy it and make ash. Well, that sounds pretty simple. That must be why we get ash all the time from these systems. If I go to material which has less vesicularity, can I do the same thing? Yes, but it's far less efficient, far more work, far greater strength, and it actually goes up to about 10 times the strength. You have to do 300 bars. So imagine the volcanic system as we believe today. There are areas which are highly vesiculated. There are other areas which are not vesiculated very much. There are even lithics. There are blocks of rocks which have fallen into the top of the magma column. If you decompress that at some intermediate value of decompression, like 10 megapascals, you will blow out this material, but you will leave that material behind because it didn't have a chance to fragment. Thanks. How fast? For some reason, this was something which always fascinated me and also something which surprised me. How much time or what speed does, if it's an explosive eruption, if you say to a chemist, I'm working on explosions, they completely misunderstand what we're talking about here because what they're interested in is detonations of chemical reactions. Those things are really fast, okay? We are actually slow. And what you can see here, if I can figure out the right button to push. Well, I use my hands. Look at the numbers. These are the results of dynamic pressure sensors. So I measure the pressure above the sample and I measure the pressure below the sample, yeah, on a microsecond time scale. And what I see is the decompression difference in time gives me effective speed, 90, 36, 18, 16 meters per second for the erosion of that fragmentation front. Think of it as an erosion or milling down into the magma, okay? These are not very fast. This number is very close to the number for you could estimate for the supply of magma from below, from a much greater depth, from a magma chamber. Many people working on ascent rates of magma, a number like 10 meters per second is absolutely normal. We say in English, a garden variety, nothing exciting. Oh, we got 10 meters per second again. What it means is that this process is possible to maintain in a steady state between two radically different things. Viscous supply of foaming magma from below coming up at 10 meters per second, and then it meets a point in the conduit where for whatever reason, decompression rate, degree of vesicularity because you're moving sideways across the diagram of strength, it hits that crisis point and just begins to crackle away and remove pieces of the pili and pieces of ash at the top. And it just stays steady state at a certain height in the chamber because you're supplying it at the same rate you're removing it. And this is how you can understand that an explosive eruption can run on for days and for weeks. If you have the unfortunate circumstance that you just match the rates. This is what I believe is behind this. We have many eruptions, of course, which do not run on for days or weeks. We have individual explosions. Dust flies off, it's over. That would be a very different dynamic regime. That would be one where something became unstable, fragmentation ran into the magma, but there was no new supply of magma. So the magma recovers, from the accident, fixes itself, and gets ready for the next one. So there are many different regimes that you can imagine, but these processes are basically on a competitive timescale. The last point is permeability, because many of you may be thinking already, and permeability is plotted here along the horizontal axis as a logarithmic property. And what is plotted here is what we call the energy density. It's just the volume of the bubbles times the pressure in the bubbles, PV. It couldn't be simpler, okay? So that's the potential energy available essentially at fragmentation, PV. And you see that it's a constant for a range of permeabilities which are very, very low. But then if we start working with rocks which have permeabilities which are high, it starts to run away. It's no longer a constant. Our assumption of a constant fails. So we're out of the regime where we can talk about a simple threshold of energy to break these rocks. And there was a whole PhD thesis which was involved in measuring the permeability of every single sample that we used in these experiments. So really the question in volcanic systems and their stability or instability is the question of whether or not the gas can get out. If the gas can get out in a simple way, the industrial factory of the volcano works. But if a crisis occurs for whatever reason, for a slope instability, for some change at the top, or for some change in supply at the bottom, then you have the industrial accident and the volcanic gas takes the mountain with it on that day. Okay, let's walk through the whole thing slowly. The advantage of slow is that you can see a lot more happening. Slow happens in nature. Here we have slow. We have a volcanic dome oozing out like toothpaste at the top of a volcanic conduit. At the bottom of that conduit, things are very viscous. At the top, you can walk across a fossil remain of a dome, and you can see faults running through volcanic magma, just like faults run through metamorphic rocks. It was obviously into the lithostatic or the lithogenic part of its failure. Three things are actually happening at the same time when we blow these rocks up. We have a viscous heating effect, which is potential, because these are high stresses. It can actually start contributing to the thermodynamic energy, the enthalpy of the system, by pumping through shearing, pumping in energy into the system. We have a structural effect, which is that the structure of the liquids, these are 4 volcanic liquids, and they all start to collapse in viscosity at a function of a certain strain rate. This onset of non-Newtonian viscosity, viscosity which depends on strain rate, is the structural destruction of the liquid. You literally, it's something which always fascinates me, you mechanically tear the thermodynamic state of the liquid apart. Talk about putting mechanics and thermodynamics together, okay? And the diffusion is not enough to put it back together again. So it's going to be complex. We also have suspension effects because carried crystals will be in the way. So we try to deform these things under much slower rates of deformation, uniaxial compression. Now we're venturing into rock deformation studies and rock physics. This is before, this is after. This is obviously not a rock, it's a standard glass. But you see, you get the compression, you get the bowling or the barreling of the sample because it's unsupported laterally. We stick thermocouples in and just try to measure the temperature. Couldn't be more simple. It's the very first high temperature viscous dissipation study. This is what a rock looks like, a volcanic rock, when you do the same thing. These are both post-deformation, of course. These are different projections of the same. You can see a barreling of the sample. You can see we're talking about composite materials, multi-phase materials. Here are the crystals, and some of these black parts here are the actual bubbles in these dome rocks. And if we squeeze them, we can watch the temperature increase. This is temperature versus strain rate. The faster you go, the more the temperature rises because the heat cannot dissipate. These are good insulators. And you start to see the temperature climb, 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 climb. If we change the temperature, we change the viscosity of a system. It really gets complex now. In other words, you can thin these things simply by heating them by flow. And we can project it all in a diagram of strain rate versus temperature. And we believe that in rhyolitic lava flows, you can be on either side of this diagram. It's complicated, but it's a beautiful, simple concept. You have the green line, which is controlling the strain rate dependence of the viscous dissipation. Will I viscously dissipate or not? And you have the blue line, which is controlling the glass transition, which I talked about since the beginning of the talk. And so depending on which line you hit first in strain rate, green before blue, blue before green, in one case, you will heat the lava, you will reduce the viscosity, and you just keep flowing. Yeah, you lubricate yourself. In the other case, before you get the chance to heat the lava, you've already broken it. And the temperature in the middle there, 590 degrees Celsius, it's not far, far, far away from glassy lava flows. Okay, the things are seismogenic. I'm not a seismologist, that's why I work with people like Alejandra Arciniega, so I don't say the wrong thing. But of course, anybody can put acoustic sensors on a machine and listen to what's happening, and we did too. And so you can measure the amplitude, you can measure the times, and you can measure the number of events of microseismic or microacoustic events as this rock crackles to its death, okay? And what you see, obviously, is something which looks like a crisis, also colored in the appropriate colors. And from the statistics of all of this, you can make an estimate of how the earthquakes of fracturing magma, magma being seismogenic, not steam explosions, not solid rock, magma breaking and magma producing earthquakes, how this might allow you to predict eruptions in the future. Okay, we're going good, but we're going fast. I'll just say a few words about an outlook on new techniques which are being applied, which we haven't worked our way through yet. The first one is on frictional heating. If there's so much friction in these magmas and in the domes of lava above them, maybe we can experimentally do that too. Experimentalists are, we would say in German, unverschämt. We're absolutely irresponsible. We try to make every experiment we can. And using what they call a welding rig, you can actually remelt rocks by frictional heating. So this is a rock that had a lot of glass in it to begin with, and if you start to heat that glass up again, it becomes a magma again. And we believe that there's evidence in the dome rocks of volcanoes for some reheating and actually remelting of the rocks on their way up through the dome. So this is a major step in complexity away from a simple model like I showed you in the beginning. Another frontier is if we can fracture these rocks and reheal them, then perhaps we need to know how much strength they have when we stick them together and pull them apart. So what you see back here are two cylinders of rock, of volcanic glass being touched with each other at high temperature and then being pulled apart again. Touched for a longer time and then being pulled apart again. That's this time, okay? You can see the strength at the beginning when they have no chance to diffusion weld to each other, if I can say those words, is very low, but it grows in, of course, over time. When the asperities disappear, when there's no void space, when this material is effectively sticking to itself, it re-obtains the strength of an unbroken rock. And we believe this happens all the time and that this is the origin of flow banding in lava flows. Flow bands are fractured and healed and strained mini earthquakes in shallow conduit processes of rhyolites. It's a fantastic notion. They will be seismogenic, but it's a question of how big the signals are. Okay? And then we get to the ash, and I have really no time today to talk about the ash. That will be my next talk, Hugo, when I come back again. The life cycle of ash. This is a diagram by Iris and Delmal, and its complexity is, prodigious, as we would say in English, and it's not complete. Understanding ash in the Earth system is something for a generation of young people, and I think that it will be something which will give us many surprises. If you talk to a solid Earth scientist and you say you're working on volcanic ash, they will simply smile and say, "Oh yeah, you mean that stuff like that, yeah?" Nobody serious, in petrology is excited about volcanic ash. If you talk to an atmospheric scientist, they're a little more interested. But again, they say, "Oh, these ash in the Earth system, yeah, once in a while, sometimes we have a little bit of ash, but it quickly settles out and it's over." Yeah? So I would argue that both of them are underestimating the role of ash in the Earth system because it's happening all the time, all over the globe. And if you measure it on anything approaching the time scale where the Earth system really changes, you should view the presence of ash in the Earth system as a constant in the background. There's always a part of the lithosphere above your head. So again, we are the experimental boys. So in this case, we try to evaluate a very important element. And this is what Anna Casas is doing today for a PhD in Munich. We take a volcanic vent, we expose ash to HCl and to SO2, and we expose them together under the conditions that we believe are the upper conduit. So when you erupt these rocks, it's not just rock, it's all these chemically active gases. And paradoxically, they are not in equilibrium anymore, even though they came from a bubbly quasi-equilibrium system, and now they've exploded into two phases. The ash cloud is coming out of the volcano. They're hot, they're reactive. You have broken glass surfaces, you have gases which can attack those surfaces, and so Anna is doing a whole PhD on how the reactivity of these systems works and what kind of influence it may have also on the biosphere. I have to jump ahead. This is the device we use. It's a simple tumbler. In order to do solid gas reactions, you have to make sure that you have a reproducible mechanical exposure of the solid surface to the gas. That's the simple, technical, hard part of doing good kinetics in these experiments. So you have to tumble the ash so it's constantly freshly exposed to the gas. Otherwise, you'll bake a surface on it, like baking some bread, and you will no longer have a simple linear kinetics to describe. Okay, I'm going to jump ahead. I apologize a little bit, but I'm winding down here. Dispersion and distribution of ash, of course, that's the huge issue when it comes to events like Auditorio Tlayólotl. Models are being produced for this kind of thing. Many people will calculate it for you, no problem. If you give them the flux coming out of the volcano, give them the meteorological conditions, they'll give you a number. But of course, they'll give you far more numbers than accuracy, okay? So it's a very, it's a delicate field to work in now because the meteorologists are convinced that they can tell you, but we're not so sure, okay? And of course, why do we question them? What would an experimentalist do? We always question these things mechanistically. So what could they be missing? Well, one thing that they can be missing is shown in this video. Look at the two little white circles and watch what happens. This is somebody standing under the ash rain in Iceland. I'll show it to you one more time, if I can. Excuse me. Here we go. 1, 2. And you see what happened. This is somebody literally standing there, seeing the ash come down. Under his feet is the geological record of the future. And these ash particles have been brought together in hundreds of thousands. They've aggregated. They touch a soft surface, like his finger, and they disappear. They disintegrate into thousands of particles. You will never see them in the geological record. So now we got a problem for the paleo interpretation of grain size distributions of clouds and ash distribution in the recent past. It's tough. And these mechanistic things now are slowly being built into models. Okay. One last area of application, and then I'll just show you a pretty picture. This one has been, if you look at my publications in Google or something, you'll see some strange things popping up, more in the direction of ceramics. It's because aircraft have a huge problem with ash. And the problem of aircraft with ash is that the jet engine is hotter than the volcano. So if you throw ash in, it's going to melt. And the ash which melts causes all kinds of problems for the system. And the biggest problem is that it actually starts to eat the ceramic coating on the turbine blades. Now you can imagine the precision of turbine technology, right? It's the pride of mechanical engineering. And if you change that geometry at all, then you're going to make these systems fail. You can do it quickly and catastrophically, as has happened. There have been 30 or 40 different events in the last decades, or you can do it chronically because you start to eat the damn turbine blades. So understanding how that works and mitigating it is something that we're working on. And we simply noticed in this business, this is the second to last slide, we noticed in this business that when you take engineers and say, we have a problem, we need to understand the stability of environmental dust in turbines. They say, we agree, let's do it. They have facilities where they throw everything into turbines. They have test facilities where they throw ice particles in there. I've been told they even throw birds in there. Anything which is a potential damage to a turbine, they'll test it on these things, okay? And then they say, okay, environmental dust. And you can imagine the conversation somewhere in a company, right? They say, okay, where are we going to get some environmental dust? And then they phone somebody up and they say, well, we have, sand. There's plenty of sand here. It's absolutely homogeneous. There's unlimited supply. I'd say it's a good thing for your test. So they say, okay. And what is the sand that they typically take? Quartz sand. So remember your petrology now. They take quartz sand and they say, this is what we're going to use to understand the effects on turbines. And of course, quartz sand is the worst possible analogy for a volcanic system because it's the furthest away in melting temperature. 1700 and something, from a volcanic glass, which simply has to soften. So we simply stepped into this business first to remind all of the people, these are annealing of ash particles of different origins, to remind all of these people that ash matters, that ash is very bad stuff, much more reactive than any of this quartz sand, and that depending upon chemistry, you have to scale the problem. You see here the same thermal path for all these samples, and you see they have very different fates. And of course, you look way over on the left, and you see these sand samples standing there. Don't move. So you would not want to take the last two frames on the left and extrapolate to everything on the right. It's as simple as that. It's embarrassingly simple what you can sometimes do in the lab to fix things or to show problems of great magnitude. And the last picture, which for 10 years I've never ceased to put into my lectures because I think it always impresses people the first time they've seen it, and that is that when you're doing experiments, you have one advantage over anybody else in the world. You're probably going to see something that you were not looking for. It's called serendipity. And sometimes when you're doing experiments, you observe things which were not engineered in, but the experiment is engineering them out, if I'm allowed to use the word like that. And we saw auto discharge of electricity off of these ash columns, which were blowing out through our tank. And we went over to, as I think I said yesterday, last Friday, we went over to the engineering department of the Technical University of Munich and said, hi, we have lightning. We don't understand anything about lightning. And they have an Institute of Lightning Research, of course, like everything else in Munich. And the first thing that the engineers in the Lightning Institute say, what kind of potential did you put on your experiment to generate the ash? Because every device that they have in their whole lab, in their whole floor, has a generation of ash by a potential, which they, with a Van de Graaff generator or with something more modern. And we said to them, we didn't do anything. We're innocent. We just made rocks fragment. And they just, the look on their faces, I can tell you, when they realized that we had come very close to a natural production of lightning without any external imposition of a source, was like, it was like an epiphany for them. They thought, wow, sit down, we need to talk about this. So it's very exciting. It goes across boundaries. This effort was one in which Miguel Auditorio was involved in the early days. Came out of this house and was sent to me by Hugo many, many years ago. And it's being led now by Corrado Cimarelli. And it's not just a pretty picture. It means that if we understand how much discharge we get correlated with how much ash we produce, then we have a proxy. We have a proxy for the flux of ash. And if we have a proxy for the flux of ash, we have something nobody else has, because it's almost impossible to observe precisely how much the volcano is producing. But if you can remotely sense it, by having antennae around the volcano and pick up the amount of discharge and have a proxy law, like all of paleoclimate, right? It all works on proxies. If you have a good proxy law, then you could say discharge intensity, amount of ash, and now you can put that most unconstrained part of dispersal laws for ash into the equation, which is the source function for the amount of ash. The most embarrassing thing about ash dispersal models is the thing you don't know is how much ash is supplying the system. And it can change. We saw in Eyjafjallajökull it went up and down. We see in the fusion rates on Etna, they go up and down from one day to the other. You need to just be there and measure it. Thank you very much. Okay.
Thank you, Don. ¿Hay alguna pregunta?
Could you talk to us a little bit more about the aggregates? Because we've been doing a lot of work on the impact of the ash on the environment in Mexico City and the surrounding area. And we've noticed that sometimes the atmospheric people say that there's no impact or that they don't have these small particles. And then we actually look at them under the probe or one of these mechanisms and then see that there are a lot of the aggregates, and that's why they think they're a lot larger particles than they actually are.
Mm-hmm. So the aggregate story, if I can say that, it's now a sub area of research with perhaps 5 or 6 people intensely looking into aggregation around the globe. It's an interesting area. It's an area of fundamental material physics because it's the question of how do you bind these particles to each other. And so there are 3 or 4 different hypotheses about what can stabilize. That these particles collide, nobody doubts. The question is, how do you get these colliding particles to stick? And so there are many different aspects which have been proposed as elements of the story, and I'll just mention 2. One is electrification. Well, we have charged particles, no question about it. One is electrification, and the second is chemical. Because we're throwing these ash particles up in a cocktail of chemicals, of gases, right? And when they cool down, where aggregation may be most effective is when we liquefy some of these things. For example, sulfate can be formed into a liquid aerosol. And these sulfate particles may act as the necessary glue for sealing these particles together. Dry it, and then you have a salt crust, which is holding these things together. So all of the work that we have done on aggregation has been so far in the direction of producing salt glue or salt crusts, which we use to stick these particles together. But I would say there's some fundamental arguments back and forth as to whether that is the primary or whether another is the primary origin of these aggregates.
I was wondering about the low fragmentation front velocity. I cannot imagine what happens in a sustained Plinian eruption in which you are having material flow at shocking velocity, sum of speed velocity, with such a low fragmentation front velocity. How do you make those things compatible?
The ejection velocities. You mean high ejection velocities? Yeah. So we get, I can tell you that in these experiments, we get the same ejection. We get hundreds of meters per second ejection velocities for these particles. Now, even though we see that the erosion of the sample from which they're produced is taking place on tens of meters per second. So we see both of those phenomena together in the experiment. So it's a question of the energy transfer from the process which destroys the material into the process which provides a fraction for kinetic energy, right? And this can have to do with essentially an energy budget. Where do I park the energy that I liberate from these materials? I have this overpressure in the bubbles. That's my source of energy. The thermal energy is not really important for us. And what is the downstream sink of the energy? So it takes a certain amount of energy to produce the surfaces, right? The fracture toughness, if you will, of the material. And it takes a certain amount of energy to liberate these particles and have them rise. And so, again, Miguel and Alejandra and others have been working on this, and Betty Shoy, of course, working on the ejection velocity as a function of all of the conditions of fragmentation that we have. But all I would say to you today is we get hundreds of meters per second. That's what you're seeing in those videos that are coming out. So.
Thank you, Professor Dingwell. I was wondering, a technical question, how can you guarantee that the results in the laboratory can be scaled into a real case? Where are the main parameters? And the second question is, in AFL Tlayólotl, there were 2 eruptions. The first one was effusive, and the second one is the explosive one that most of we know. It's possible in a laboratory to try to reproduce these rapid changes in the magma properties that produce rapid change in the kind of eruption that we have.
From effusive to explosive?
Yes.
Yeah. Okay, the first keyword, scaling. When we started doing these experiments, the generation before us from, say, 1970 to 1985 were all fluid dynamicists, right? Sparks, Jopar, Huppert, all these people were working as all fluid dynamics. So they were doing things in a continuum where they had phase changes like bubble rise, crystal fall, acceleration in a continuous viscous situation. And so they were always taking great care to scale through the laws of fluid dynamic analog experiments using analog materials. And when we first started doing these experiments, everybody told me, Don, this won't work because you can't scale things with a very high viscosity. This viscosity will throw you out of the scalability to nature every time. If you get the viscosity right, what sounds like intuitively what you would do, you will lose it on length scale, you will lose it on time scale, and so on and so forth. That is true if we're talking about fluid dynamics of systems in a continuum, okay? But what we're talking about here is fragmentation length scale. And the fragmentation length scale is something which is controlling this slow speed, which we see. This is what we believe. It's the time it takes to do the work to actually physically separate the particles. And so we ask ourselves the question, what is the characteristic length scale of the fragmentation, and can we get that right, or are we wrong? And what I would say to you is the average spacing of crystals and the average spacing of bubbles in the magma must surely be the most important length scale for the failure of this material. When you hit a bubble, the job is done for you as long as you cross the bubble. All you have to do is get to the other side. So it's my firm belief that the scale that we have to pay attention to in these experiments is the crystal size and the bubble size in the magma. And so the only way we can guarantee that we're doing anything roughly approximate is to make sure that our samples are much larger than the bubbles or the crystals. You know, this classic argument in rock physics that you must go sample must be 10 times as big as the crystallinity, otherwise you're going to get erratic results. So this is the way that we respond to this question of scaling. It is true that we are not worried about the fluid dynamic scaling, which is a literature, as you know, on these experiments. We're worried about the scaling of the length scale, which is characteristic for failure of these materials. We have tried to test it, of course. We have tried to respond to this question by changing the diameter and by changing the length from the vent. When we change the length from the vent, we change the decompression rate, because that's the nature of the decompressing gas running into the tube. That makes a difference that we can understand simply based upon the decompression rate which hits the sample, which is quick if we're close to the failure of the membrane, and which is slow if we're far away from the membrane. The other thing we changed, but only up to a factor of 2 because of experimental limitations, is the diameter. And it does make a difference in detail for the, of course, for the largest part. The largest pyroclasts we get are the diameter of the sample. This is clear. So it unquestionably makes a difference, for example, in our grain size distribution if we double the size of the experiment, because we get particles on the coarse end which are twice as large in diameter. So there's no question in the simplest of analysis that makes a difference in detail. But we think that we can scale these distortions in grain size variation according to the size of the fragmenting system. I mean, ultimately, we want to go out in the field, look at the particles, and see if they look like our experiments, our experimental particles. And over the course of the couple decades that we've done this, we've had field volcanologists walk up to us and say, you know, in the 90s, people would walk up to us who were monitoring Montserrat, and they would say, you know, Don, despite the skepticism towards your work, I have to tell you that we walk over the fresh surfaces of ejecta in Montserrat and we pick up disc-sized particles that look just like the stuff you're producing in the lab. It's the kind of thing they whisper to you in the corridor because the boss didn't like it. But so this kind of thing happens. Huh? So we're always trying to compare and play the game of projecting two pieces and asking you which one is the natural one. And we're fairly close. Now, your second question was the effusive to explosive, right? Yes, we can go there. You may have been frustrated by what I was talking about here. I don't know, because we're obviously way over into the brittle regime. We're not having any we don't believe there's any appreciable viscous response when we fragment these things. We think it's crystal clear. All the energy goes into brittle fragmentation. Yeah? You can now think about the experiment where you step back in strain rate so that you allow a creeping in of the viscous fraction of deformation. And this is what we're trying to do right now with magmas. It's been done already with analog materials by Miya Ichihara in Japan. She did experiments where she adjusted the viscosity of her analog materials, where she had the freedom to do so, and she backed off her viscosity so that she would have bubble growth and fragmentation interfering with each other. And that is what probably is the most accurate thing for nature. We see drastic examples of bubble deformation, which is interrupted by fragmentation. When you look at tube pumice, for example, where the tubes are 100 or 1,000 times as long as their diameter, it's clear that these bubbles have been through, hell. They've been through an agony of deformation, and they've been chopped by the fragmentation event. So I think you're right there that there's no doubt that we have to approach this effusive explosive boundary. You hear me now talking about it from a materials point of view, as always, because that's what we do in the lab. Of course, conditions at the volcano may, in their variation, be sufficient for you to switch from one regime to another. Many of us are searching the holy grail of what causes it to switch from effusive to explosive. Either the system changes, or the material response changes, one or the other. Certainly, let me take that back. Either the system changes or the material properties change. That the material response changes is clear. It explodes or it doesn't explode. And it could be a combination of both. When I was talking about the magma coming up through the vent at a certain rate and being eroded at a certain rate, and I was saying many things could lead to the localization of where it just dies. It could be vent geometry. It could be any kind of stress localization that somebody in mechanical engineering would love to calculate for you. Or it could simply be that the lava loses too much water, becomes too brittle, and dies right there. And of course, it can be both. And, understanding whether it's both or one or the other, this is probably something we need the volcano monitoring for, and sufficient data from seismicity and other such things to try to produce a consistent model in different examples.
Don, thank you very much for this wonderful presentation, wonderful exposition of the whole thing. I see in your talk a good news for seismology, because seismic waves are much faster than all the velocities you mentioned, and I see in this field an opportunity to new techniques to sample what is happening during eruptions, before them, just to sample how materials propagate. Even nonlinear materials may be linear in the very high frequency range. You're looking at, I think I see in all your slides a nice opportunity also for seismology proving of the volcanic phenomena, and a great opportunity. Thank you very much for all your comments.
Thank you. Yeah, this is an opportunity which people like Alejandra are going to be the ones to advance. Absolutely. Alejandra has been putting acoustic sensors on these experiments now, which again, for many seismologists, they would say, wow, these are experiments. It's interesting, but we need to measure in the field. But of course, if we can completely tame our experiments in terms of their seismicity, this is what Alejandra is doing, then we know how far we can go, and we know where we can go and where we cannot go.
Hello, good afternoon.
Hi.
I have a doubt about the samples that you have used on your experiments. Have they been recollected in field, or how do you?
Yeah, good question. I was talking the whole time about samples. You might as well ask me what we're using. Basically, in the beginning of this work, like 25 years ago, I said we're going to use both. And what did I mean? I meant we're going to build magma from silicates, real stuff, but build it, and we're going to go to the field and take it, okay? And only when we see that these two kinds of materials are giving us convergent behavior do we believe that we can build it. Fair enough, right? So there's two fundamental philosophies, and I should show this when I give this talk. First of all, we go to a typical way we collect the sample is we go to a pyroclastic flow in the field, a fresh one, hopefully. We pull out a block of it, which is basically a large end of the grain size distribution. And we cut it to a transportable size, take it back to the lab, drill it out, make it the size we need for our experiments, and put it back under pressure. The argument is that the best place to get a representative part of a volcanic dome is not on the, well, let me put it this way. The best place to get a representative part of the volcanic dome, which is fresh and magmatic, and therefore tells the story of deeper processes, is to pick up a block from a fresh pyroclastic flow, because it's been thrown down there in a matter of minutes, and nothing has happened to it since. If you go to the top of the dome, all the processes of low temperature transportation, gas transportation, and corruption of the initial state of the magma are there, and you don't get anything fresh. You get sulfur and everything, and so on and so forth, right? So this is how we get the samples from the field. Where do we get the other samples? It takes a little bit of time to explain it, but basically back in around 2000, we perfected a technique for starting with reagent grade chemicals, putting them together, melting them to make a glass, taking this glass, putting it under pressure, putting water, hydrating it in, taking it out, putting it in another device and decompressing it at high temperature and allowing it to foam and produce a pumice, and then fragmenting that pumice. It sounds complicated, and therefore it was only one postdoc that I could convince to do this for 2 years. But as we speak now, we're beginning to pick this up again. So I could show you pictures of tube pumice. Unfortunately, I won't be able to find them, where you would be astonished to hear that we made this tube pumice in the lab from silicate at high pressure with water and during decompression. So we can engineer these materials. It's a lot of work, and eventually it comes down to the question of you engineer enough material to prove that you can generalize the results of the natural material, and then practically speaking, you run with the natural materials and the complexity that you know is there, because practically speaking, reproducing every one synthetically would slow down your research quite considerably. But we are interested and do believe in convergence of the synthetic and the natural approach. And if you would ask anybody else who would stand here as an experimental volcanologist, there are a few others, almost nobody else would do that. It's because we had the resources, the time, and the people that we were able to do it.
Thank you.
Yeah, thanks.
There are several students here, and recently doctors from students of ours. So it will be interesting for everyone to hear that Professor Dingwell is always open for new ideas. If you have any experiment in your mind, perhaps Don will be very happy to invite anyone with a good idea.
Yes, and let me say that for the next 5 years at Munich, we're in good shape. We're in good shape financially and in terms of opportunities. We got a new grant from the European Research Council. It's our second one, which means that there's very few people in Europe who get that. It's because of what we were able to do in the last 10 years, and it gives us the opportunity for the next 5, 6 years. So, frankly, if you have a well-framed question, and that's something which is usually a conversation, right, between the experimentalist and the person with the idea, then we probably have the resources to if it's a good one, then we have the resources to do it, and we have the resources to bring people to Munich, at least to design it, and possibly even to stay longer. Thanks for mentioning that, Hugo.
Ok, pues vamos a despedir al doctor Dingwell con un aplauso.
Thank you.